Another factor that influences the character of covalent bonds is something called electronegativity. And this is the ability of atoms in a molecule to attract the shared electrons in a covalent bond to themselves. So we can think of bonding as existing on a spectrum between fully nonpolar covalent, which are just electronically symmetrical, where the electrons are shared completely equally between the two atoms, and fully ionic, where the electrons are not shared at all. We have complete electron transfer from one atom that becomes a cation to another atom that becomes an anion. Now, many bonds exist somewhere along this continuum, where the electrons are shared between the two atoms, but it's not an equal sharing. And if we have unequal sharing of electrons, but still some sharing, this is called a polar covalent bond, because an electric dipole exists. If the electrons are more attracted to, say, atom X than they are to atom Y, like you see in this diagram, then atom X will have a partial negative charge, and atom Y will have a partial positive charge. That's what that lowercase Greek letter delta means, is partial charge. Since these atoms are sharing electrons, the charges are partial. We don't have actual ions, but there is still some positive charge associated with atom Y and some negative charge associated with atom X, and so we have an electric dipole that points away from atom Y and towards the partial negative charge on atom X there. Now, electronegativity is what determines how polar a bond is. So, in the case of atoms Y and X in this diagram here, atom X attracts the electrons more strongly than atom Y in the bond between them, and so atom X is said to be more electronegative than atom Y is. One way that your book uses to represent how electrons are shared in covalent bonds is with what are called electron density maps. So these are color-coded ways of showing you where the electrons are in molecules, including whether they're more attracted to one atom or another. So a good example of a nonpolar molecule is something like chlorine, where this is a diatomic element, so it consists of two chlorine atoms bonded together. And in fact, anytime you have two atoms of the same element bonded together, since those two atoms should have the same electronegativity, typically you'll have a nonpolar bond between them. And in fact, for diatomic molecules like Cl2, where the two atoms are identical, they're going to be completely nonpolar because both chlorine atoms are equally capable of attracting those electrons that are shared between them. And so we have a nonpolar covalent bond between those two atoms and a moderate amount of electron density around each chlorine atom, as represented by the greenish-yellow color surrounding each atom in the diagram on the right. An example of a polar covalent bond might be one between a hydrogen atom and a chlorine atom in molecular hydrogen chloride. So this is a covalent molecule in the gas phase. If it's dissolved in water, it's hydrochloric acid and it's split up into ions, but if we just assume that we're dealing with a covalent molecule, we would have a covalent bond. And it turns out that chlorine is more electronegative than hydrogen is, and so the electrons in that bond will be more attracted to the chlorine atom than they will be to the hydrogen atom. As a result, the hydrogen has a partial positive charge and the chlorine has a partial negative charge. We can see this in the electron density map on the right. The chlorine atom has a higher density of electrons around it, as indicated by the red color, and the hydrogen atom has a lower density of electrons around it, as indicated by the bluish color. And finally, if we look at something like a true ionic bond, like say between a sodium ion and a chloride ion, the electron density map would show us that the electrons are pretty much completely localized around the chlorine atom, and there's not really much sharing going on there at all. So how can you actually determine if a bond is polar or not on your own without me telling you that, for instance, chlorine is more electronegative than hydrogen? So there's actually a periodic trend associated with this, as shown on this chart, and it is kind of the opposite of how atomic sizes work. So as you go towards the right and towards the top of the periodic table, we're going to encounter higher electronegativity values. And as we go towards the bottom left, where the larger atoms tend to be, we're going to have lower electronegativity values. And like a lot of stuff that we covered in the previous chapter, the exact values of the electronegativity on this periodic table are not particularly important. It's just important to know which atoms are more electronegative than others. And in terms of main group elements, the trend that things become more electronegative as you go towards the top and towards the right is more or less without exception as far as we're concerned. Since the noble gases don't form compounds, we can kind of ignore them for purposes of ranking electronegativity. And you can see that fluorine here, with an electronegativity value of 4.0, is the most electronegative element in the periodic table. So any bond between some other element and fluorine will always have the electrons in that molecule more strongly drawn to the fluorine than to the other atom, no matter what that other atom is. Other very electronegative elements, although not quite as electronegative as fluorine, include nitrogen, oxygen, and chlorine. I've alluded to this before, but there are some significant differences between covalently and ionically bonded substances. So besides the obvious chemical difference in terms of the nature of the bonds, the physical properties of ionic versus covalent compounds are often quite different. So for instance, if we compare sodium chloride and hydrogen chloride, two substances with chlorine in them, they have roughly similar formula masses. They're not that close, but they're close enough that we can attribute most of these differences to the type of bonding and not due to the difference in the formula mass. So hydrogen chloride, as a pure substance, is a colorless gas that boils at negative 85 degrees Celsius, whereas sodium chloride is a white solid that doesn't even melt until over 800 Celsius. And this is typical of covalent versus ionic substances. Covalent substances can be liquids or solids in some cases, but they are almost always pretty low melting compared to ionic substances, which typically have very high melting points and are more or less always solid at room temperature. All right. Next, let's get into electron-dot structures, and these are also called Lewis structures. So electron-dot structures are ways of representing the distribution of electrons in covalent compounds. And the way this works is that we actually, as the name implies, represent valence electrons with individual dots. Now, we only represent the valence electrons because core electrons don't involve themselves in covalent bonding in any way. It's only the valence electrons. So to start with possibly the simplest covalent molecule, hydrogen, with two individual hydrogen atoms bonded together, each individual hydrogen atom on its own has one unpaired electron, as indicated by the pink dot next to each H there. And if those come together to form a hydrogen molecule, the two electrons, one from each atom, will come together to form a pair. So they pair together just like two electrons in the same orbital paired together. And these form what are called a bonding pair of electrons between the two hydrogen atoms. And in terms of orbitals, this actually involves direct overlap of the two hydrogen 1s orbitals where those electrons are contained. If we look at the structure of something a bit more complicated, like say a fluorine molecule, fluorine's another diatomic element, so two fluorine atoms bonded together. This one's a bit more complex because we have 7 valence electrons per atom. So the electron configuration for fluorine is helium, 2s2, 2p5. So the 2 s electrons and the 5 p electrons come together to give you 7 valence electrons per atom in total. Now, when assigning electron dots to atoms in an electron dot structure, you have 4 places that you can place electron dots: above, below, to the left, and to the right. Now, it doesn't matter sort of where you put these, except for the fact that you need to basically treat those the same way you do boxes in an orbital filling diagram, where you put down 1 electron in each of those spaces before you start pairing electrons together in each space. And each of those 4 regions can hold up to 2 electrons. So in most ways, you can treat those just like representations of orbitals. So if you assign the 7 electrons to those 4 regions around your fluorine atom, you'll end up with 3 pairs and 1 unpaired electron per fluorine atom. The paired electrons are in black, and the unpaired electrons on the individual atoms are in pink. When those come together, just like in the case with hydrogen, we still have 1 unpaired electron per atom, and so we can bring those 2 pink electrons together to form another bonding pair between the fluorine atoms, but we still have those pairs of electrons that are not involved in bonding because they were already paired on the individual atoms. And these are called non-bonding pairs, or more commonly lone pairs. And notice, looking at the fluorine molecule, that if we count the bonding electrons, the ones in pink, towards the electron count of each fluorine atom, then each of those atoms is now surrounded by 8 valence electrons. Each fluorine atom has access to 3 lone pairs, or 6 total electrons in black, and then the 2 electrons in the bonding pair for a total of 8. And so just like individual atoms that form ions want to follow the octet rule, so do atoms in these electron dot structures. We can also look at the diatomic molecules O2 and N2, the elemental forms of oxygen and nitrogen respectively. And if you follow the rules for assigning electrons, where, again, for the individual atoms, the paired electrons are in black and the unpaired are in pink, you can see that for oxygen, each atom has 2 pairs of paired electrons for a total of 4 electrons in black, and 2 unpaired electrons. Since we have 2 unpaired electrons per oxygen atom, each oxygen atom can share 2 of those electrons with the other oxygen atom. And so we're going to form 2 bonding pairs between those 2 atoms, since we'll have 2 unpaired electrons from each oxygen to do that, and each one can pair with an unpaired electron from the other oxygen. And so since we have 2 pairs, or 4 total bonding electrons there, we have what's called a double bond. And while the bonds here are shown as dots, it's much more common as we move forward to represent a bonding pair of electrons not by 2 dots, but by a single line between the 2 atoms. And so if we have something like 2 bonding pairs of electrons, or a double bond between 2 oxygen atoms, we could represent that with 2 parallel lines between the 2 oxygens. So if you see something like that, you would need to know that that represents 2 bonding pairs, or 4 total bonding electrons between those 2 atoms. And also, if we look at nitrogen, where each nitrogen atom has 1 pair of electrons in black, and then 3 unpaired electrons in pink, we now have 3 electrons from each atom that we can pair together, so that's going to give us 3 bonding pairs of electrons, and hence a triple bond between the 2 nitrogen atoms there.